Hey everyone! Back in school, most of us learned the same little formula. The circumference of a circle equals 2 times pi times the radius. And pi, we were told, is about 3.14. Nobody really questioned it. You just wrote it down, plugged it into a test, and moved on. But stop for a second. Why 3.4? Why not a clean number like 3, or 3.5, or 4? If you were designing the universe from scratch, would you really pick a number that never rounds off, never repeats, and never ends? That is exactly what pi is. Its digits just keep going. 3, 1415925, and on, forever, with no pattern anyone has ever found. Here is the part school never really explained. The definition you memorized, circumference divided by diameter, only tells you how to measure pi. It does not tell you what pi actually is, or why it has to look like this. So let's go back to the very start, and ask the question properly this time. Picture trying to bend a perfectly straight ruler into a perfect circle. It never quite works. Straight and curved are two different kinds of shapes, and something has to give when you force one into the other. That something is pi. Take any circle you like. A coin, a bicycle wheel, a circle the size of a football field. Measure the distance around it, then measure straight across through the middle. Divide the first number by the second. You always land on the same value. 3.14159, no matter how big or small the circle is. If you ever asked why in school and just got told to memorize it, you were asking the right question. Pi was not invented by a mathematician sitting at a desk. It was discovered, the same way we discover a law of physics. It is a barrier built into flat space itself, one that shows up the moment you try to compare something straight to something round. Circumference divided by diameter is only the surface of it. That ratio is just where pi happens to leave its fingerprint. What pi actually is runs deeper than that. And to see it, we need to go back to the people who first tried to pin this number down. People have been hunting this number for thousands of years. In 1936, archaeologists found a clay tablet near the ancient city of Susa, in what is now Iran. It had been written by Babylonian mathematicians sometime between 1900 and 1680 BCE. On it, they used pi as 25/8, which comes out to 3.125. Good enough to lay out a circular field, not exact, but close. Around 1650 BCE in Egypt, a scribe named Ahmes copied down a mathematical text we now call the Rhind Papyrus. His method for circles works out to a pi value near 3. 16. Different civilization, different tools, same struggle to pin down the same number. Then, around 250 BCE, the Greek mathematician Archimedes changed the approach entirely. Instead of measuring string around a circle, he trapped pi with logic. He drew a polygon just inside a circle and another polygon just outside it. The circle's true distance around has to sit somewhere between the two. Then he kept adding sides, 6, 12, 24, all the way up to 96 sides on each polygon. By squeezing from both directions, Archimedes proved pi has to fall somewhere between 223/71 and 22/7. That pins pi down to somewhere between 3.1408 and 3.1429, accurate enough that people still round pi to 22/7 today. Centuries later, around 480 CE, a Chinese mathematician named Zu Chongzhi pushed this same polygon idea further than anyone thought possible. Working with nothing but counting rods, the standard calculating tool of the era, he used a polygon with over 12,000 sides. His result nailed pi to 7 correct decimal digits, landing it between 3.1415926 and 3.1415927. He also left behind the fraction 355/113 as a strikingly accurate shortcut. That record stood for about 900 years. But notice something. Every single one of these people, across 4 different civilizations, only ever produced an approximation. More sides on the polygon still would not have given a perfect, final answer. Why not? Why does adding more sides, more digits, more effort never actually finish the job? Let's go back to that idea of squeezing a circle between 2 polygons, because it holds the first real clue. Take a hexagon, 6 straight sides. Now double it to 12 sides. Then 24, then 48. Keep going, 1,000 sides, 10,000 sides. Watch what happens to the corners. They get smaller and smaller, softer and softer, until eventually your eye cannot tell the polygon from a circle anymore. In the limit, the straight edges melt into one smooth curve. Pi is basically the price you pay for turning something straight into something round. It measures exactly how much curving costs. Now here is a second way pi shows up, and it has nothing to do with degrees. Draw a circle with radius r. Take a piece of string exactly as long as that radius, and lay it along the curved edge of the circle. The angle it carves out at the center is called 1 radian, about 57 degrees. Keep laying more of these radius-length strings along the circle. To go all the way around once, you need about 6.28 of them. To go exactly halfway around, you need 3.14159 of them. That is not a coincidence. That is pi. Half a full turn equals pi radians. A full turn equals 2 pi radians. Pi is not just about circles sitting still. It is the natural unit for rotation itself. Compare that to the 360-degree system most of us learned in school. Historians think that number traces back to ancient Babylon, where a year was treated as roughly 360 days. It is a convention, borrowed from a calendar. Radians are not borrowed from anything. They come directly from the circle itself. This is why pi keeps appearing in places that have nothing to do with circles on paper: sound waves, a swinging pendulum, alternating current in a wall socket. Every one of those is really just a point spinning around a circle in disguise. Wherever something turns, pi is the ruler measuring how far it has turned. So we know what pi measures now, but we still have not answered the real question. Why does it never end? Why can't we just write it as a fraction and be done with it? The answer comes from a surprisingly simple game with squares. Here is a simple game that gets to the heart of it. Take a rectangle and try to fill it completely using only squares, as few sizes as possible. Cut the biggest square that fits, then look at whatever strip is left over, and cut the biggest square that fits in that strip, and keep going. Try it first with a rational number, a plain fraction. Take a rectangle 22 units by 7 units. Cut 3 squares that are 7 by 7. That uses up 21 of the 22 units, leaving a thin strip just 1 unit wide by 7 units long. Now cut squares 1 by 1 into that thin strip. Exactly 7 of them fit, with nothing left over. The rectangle is completely filled. The game ends in 2 clean steps. That is what it looks like when a number is rational, a fraction of whole numbers. The cutting always finishes. Now try the same game with pi. Take a rectangle pi units by 1 unit. Cut 3 unit squares. That leaves a thin strip about 0.14159 units wide. Cut squares that size into what remains. 7 of them fit, leaving an even thinner sliver. Cut squares that size into the new sliver. 15 fit this time, leaving a sliver thinner still. Keep going, and the same thing happens again and again. Sounds almost crazy, but that is the whole answer. No matter how far you zoom in, whether you are cutting pieces the size of an atom or smaller, there is always a leftover strip demanding an even smaller square. The cutting never finishes. A number is irrational exactly when this square game never terminates. That endless cutting is not a flaw. It is the definition. This is an intuitive way to feel why pi behaves this way, not a strict mathematical proof. The full proof came in 1761, when Johann Heinrich Lamberts showed it using a different tool, a continued fraction built from the tangent function. He proved that whenever a non-zero fraction is plugged into tangent, the result comes out irrational. Since the tangent of pi over 4 equals exactly 1, a rational number, pi over 4 itself cannot be rational either, which means pi cannot be rational. It sounds backwards, using a result about tangent to explain a visual game with squares, but both are pointing at the same fact from two different directions. Pi does not repeat, does not terminate, and never settles into a clean fraction, because there is no clean fraction hiding inside it to find. Everything so far has been true in a flat world, a sheet of paper stretching out forever with no curve to it. What happens if we take pi out into the actual universe, where space is not always flat? Picture a circle drawn on the surface of the Earth, something enormous, like a giant circle traced around a whole continent. The circumference is easy enough, you just walk the curve. But the diameter now has to be measured straight through the middle, along the curved surface of the planet, not through the ground beneath it. Because the Earth bulges outward, that surface distance across the middle ends up longer than it would be on a flat map. Divide the circumference by that stretched-out diameter, and the answer comes out a little less than pi. Now imagine the opposite kind of surface, shaped more like a saddle, curving away from itself instead of curving around. Draw a circle there, and the ratio flips the other way. Circumference divided by diameter comes out a little more than pi. Neither of these breaks math. The abstract number pi, 3.14159, never changes. It is fixed forever, the same in every universe you could imagine. What changes is the ratio you actually measure, once you leave flat space and step onto a curved surface. Flat Euclidean geometry, the kind from your school notebook, is really just one special case among many possible shapes of space. Einstein's general relativity takes this even further. Around something incredibly massive, like a black hole, space itself bends. If you could measure a circular orbit around one and divide its circumference by its diameter, the number you would get drifts away from pi as well. Pi on paper never moves. But out in the real universe, the ratio you can actually measure tells you something else entirely. It tells you whether the space around you is flat or curved, and by how much. So what is pi, really? It is not a mistake in the design of the universe. It is not an ugly, unfinished number that mathematics somehow got stuck with. Pi is the unavoidable cost of comparing something straight to something curved, in a space that happens to be flat. Its endless digits are not chaos. They are what a perfectly consistent system looks like when you try to squeeze a circle into a ratio of whole numbers, and it simply refuses to fit. That refusal is not a flaw. It is pi being exactly what it has to be. Math was never really a pile of formulas you had to memorize for a test. It is a system where every honest question you ask, even one as old as third grade, deserves a real answer, not just an instruction to memorize. If this changed the way you think about a number you have known since childhood, consider subscribing to Axiom. There are more of these hiding in plain sight, and if you want to know where we go next, drop a comment. Maybe it is time to look at E, or the golden ratio. Numbers that seem just as ordinary until you actually ask why.